Let's take a peek into the nature of covalent bonding. This presentation will be divided into two micro-lectures, one of which will cover the basics and the other of which will cover the exceptions. Be able to define single covalent bond, when two atoms are held together by a pair of electrons. Structural formula. This is a representation of the covalent bonds as dashes between atoms. Unshared pair. This is when you have a pair of valence electrons that are not part of a covalent bond. Double covalent bond. This is very much what it sounds like. It's two bonds together, so 4 electrons being shared between two atoms. Coordinate covalent bond. This is where one atom is sharing both electrons with the other. Polyatomic ion is pretty much what it sounds like. It's an ion that's made of multiple atoms. Bond dissociation energy is how difficult it is to break a bond. Resonance structures are when you have two possibilities of how to draw bonds, and you can kind of alternate between them in the molecule. This fulfills HSPS 1-1 of using the periodic table to predict how elements work, and HSPS 1-4, which develops a model to illustrate that the release or absorption of energy from a chemical reaction system depends on the changes in total bond energy. See that bond dissociation energy above. Be able to draw structural formulas and electron dot diagrams for covalently bonded molecules. Let's look back at the octet rule. Remember that noble gases are very stable. They have filled s and p orbitals. They have 8 electrons in their valence level. You can draw electron dot diagrams for helium, neon, and argon, and what you'll see is the standard 8 dots around the chemical symbol. But how do you fill these if you don't have enough? Well, here we have covalent bonds. In fact, single covalent bonds. This is where a pair of electrons is being shared, allowing the atoms to fill the octet. Now we're going to draw that as a line between two atoms, and that line implies 2 shared electrons. So take a few to draw the electron dot diagrams for hydrogen, fluorine, and iodine, and then draw molecular diagrams for H2, F2, and I2. Now, structural formulas, this is when we're going to use covalent bonds in place of the electrons. So you can see the electron dot structure for cyclopentane there. Not cyclopentene, it's actually cyclopentane. Anyway, you can see the dots are, that'd be difficult to draw. That'd be a pretty boring way of showing it, and it takes a lot of writing. A simpler way is just using these lines to show the bonds. Remember, each line is 2 shared electrons, and all the electrons are being shared here, so it's all lines. This is how most people are going to just draw these. Now you can draw the structural formulas for hydrogen, fluorine, and iodine. You have those diatomic molecules. You're going to see that it's just H-H, F-F, and I-I. That's just a simple way of making this look. But not all electrons are going to form bonds. If you draw electron dot structures for oxygen and for hydrogen, you're going to notice oxygen would need 2 more electrons to make an octet, and hydrogen needs 1 more electron to make its filled S shell. H2O has 2 electrons shared from oxygen and 1 from each hydrogen, so you can draw that here. But there are these unshared pairs on the oxygen. Those are non-binding pairs. We can also draw molecular diagrams for NH3 and CO2, seeing where the non-bonding pairs of electrons are. So how many bonds can be formed? So draw the electron dot diagrams for carbon, nitrogen, oxygen, and fluorine. Predict how many bonds each should form, and then draw the molecular structure for CO2. What you might notice is you have 2 oxygen there and 1 carbon. How do you get a total of 4 bonds?